All right, so let's define some trig functions analytically. So what I mean by that is we're just going to define it kind of within the coordinate plane for now. This is not sort of like the only way that we'll define it. Later we'll define it maybe a little bit more generally outside of the coordinate plane. But for now, just take any point in the coordinate plane, x, y, and I put mine in quadrant 1, but it applies anywhere. You can choose any old point, and we'll just draw a little line connecting that point to the origin. And we'll also drop a perpendicular from that point to the x-axis. Okay, so there it is, perpendicular. So now we have this sort of right triangle where the bottom leg is a length of x. It has a height of y. And then the hypotenuse, I'm going to label it as r, but r, we can calculate that since we have x and y, and this is a right triangle. We can just use the Pythagorean theorem. And here, in particular, we're taking r to be essentially a distance, like a distance from the origin to this point. So r is always going to be positive, so when we solve for r, we only need to worry about the positive root. So the square root of x squared plus y squared is what r would be calculated as, but for now we're just going to leave it as r. And from this, we can define our 6 trig functions. So first of all, since they are functions, they take something as an input, and you might be wondering, well, what is the input here? Because I just chose some random point on here. So it's no longer the case that like x is necessarily the input. So what is the input? The input is the angle that this line, the radius, or maybe the modulus if you want to call it, the angle that this produces. So we're now essentially thinking of this point as having been created by this angle. So, and the angle is our input that we define the trig functions by. So those functions are the sine of theta. And the sine of theta, we define that analytically, we define that to be y divided by r. So whatever this y value is, y divided by r is sine theta. This is a definition. This isn't being derived from anywhere. This doesn't follow from anywhere. We're just saying, hey, call this ratio y divided by r. We're going to call that the sine of this angle that is formed, because this angle uniquely designates x, y, and r. So sine theta is y over r. Cosine of theta is x over r. Tangent of theta is y over x. So those are the 3 basic trig functions, and then of course we have 3 more trig functions, which are just the reciprocals of these, and there's nothing more to them beyond that. They're just reciprocals. So cosecant of theta, which is the reciprocal of sine theta, and I think that's sometimes confusing for people, just because you might sort of intuitively think that the reciprocal of cosine is cosecant, since they both start with co. It's not the case. It's a little bit confusing. At least in my opinion, it's always a little bit confusing. Like I have to double check myself anytime I'm working with cosecant or secant, just to make sure I'm using the right reciprocal. Cosecant is the reciprocal of sine, which means that the cosecant of theta is r over y. The secant of theta is the reciprocal of cosine of theta, which means that it is r over x. And cotangent of theta is the reciprocal of tangent. So it's x over y. And this is how our trig functions are defined, just analytically. So if we had something, let's just say we take the point as like an example. Maybe we say there's some angle theta, the terminal side of the angle theta passes through the point, what did I say, -2,5. And then we want to evaluate all 6 trig functions for theta. So almost always, I mean, even if it feels like you don't need to, I think that it's really smart to make some kind of visual. It just gives you a better idea of the problem that you're solving. And sometimes there might be some nuances, some little details that you might overlook if you're doing everything like in your head, that a graph might make very obvious. So the point -2,5, I don't need to be precise, it's like here. Yeah, so that's 5. Here's -2, so yeah, -2,5, of course. And yeah, but just based off of this, you can start filling out all of the 6 trig functions. You have to solve for r, of course, but that's not hard because r is just based off of x and y. So you can even right here just start kind of plugging and chugging. But me, I still prefer, and I think that this is smart just for looking forward. Still go ahead and connect this point to the origin, make the right triangle, because trig is all about triangles. So we'll see how well I line this up. It's close enough. Yeah, it's pretty good. So again, that's a right triangle. And here's r. Let's calculate r really quick. So r is going to be x squared, so -2 squared is 4 plus y squared, which is 25, so square root of 29 is r. And just to make things really easy on me, x is -2 and y is 5, just so everything is just kind of like listed out for me. And just kind of for completeness, for like the understanding side of it, this is actually not necessary for writing out what these evaluate to, but just for the understanding side of it, theta always starts, the initial side is always the positive x-axis. So theta is going right here. This is the angle theta that we're talking about. Okay, so then sine theta is equal to y over r, so 5 over root 29. And for completeness, this is not really the way that we want to represent this. I mean, technically this answer is correct, but most cases you're going to be expected to rationalize your solution. So in this case, it's multiplying top and bottom by root 29 to get rid of the root in the bottom. So this is 5 root 29 over 29. Cosine of theta is x over r, so -2 over root 29. And again, after we rationalize, it's going to be -2 root 29 over 29. Tangent of theta is y over x, so -5/2. And then the others are just reciprocals. I didn't save myself enough room, so I'll write it over here. Oops. Let's see here if I can do this a little bit. Yeah. Sorry about that. There it is. Okay, so cosecant is the reciprocal of sine, so root 29 over 5. Secant is the reciprocal of cosine, so negative root 29 over 2, and then cotangent is the reciprocal of tangent, so -2/5. let's see, I keep going off the screen a little bit, sorry. There. Okay. So that's how we would go about solving that. What else do I have? Yeah, so another way that this question might kind of come up is rather than giving us a point, we might be given like an equation. So something like suppose an angle theta has a terminal side given by the equation 3x plus 5y equals 0, where specifically x is greater than or equal to 0. Well, on the one hand, what you could do is you can just pick a point and then do the exact same thing as what we already did. Like you could choose, you don't want to choose x or y being 0. Let's see, what did I end up choosing? I think I chose x equals 5. Yes. But what you can also do, rather than just trying to strategically guess a point or choose a point, and in particular, the reason I chose 5 is because it allows me to work with whole numbers. You could choose anything. Like you can choose x equals 1, which would mean that y is going to be negative, 3/5, right? I'm doing it off the top of my head. But I don't really want to work with fractions all that much. I don't like working with them. So instead, what I do is I just solve this thing out for y so that I know what the line is. Y equals, negative 3/5 x. And again, x is restricted to being greater than or equal to 0. Yep. And then from this, you can see that if we choose x equals 5, it cancels out the fraction. So if x equals 5, then y is negative 3. So in other words, this goes through the point 5, negative 3. Right, 15, minus 15, 0, And then now it's the exact same. It's been reduced to the previous problem that we looked at. Notice too, just really quickly, one thing that I'll point out is, so in our definitions here, these are fractions, and I really should have been a little bit more diligent with this, because tangent of theta, for example, is equal to y over x, assuming that x is non-zero. That's the big problem that's going to come up, especially in these reciprocals. We don't have to worry about it with sine and cosine, because if x or y is 0, the whole thing cancels out, and r won't be 0, assuming that either x or y is non-zero, then r is going to be non-zero. So those ones you don't need to worry about, but in these other ones, we have to worry about a 0 in the denominator. So what happens, that raises the question, what happens if there's a 0 in the denominator? Well, it's exactly what you would expect to happen whenever there is a 0 in the denominator, which is that the function becomes undefined. So just kind of a quick look at what that would look like. Suppose that, and these are called quadrantal angles, when the angle falls on one of the axes, meaning that either x or y is 0, those are called quadrantal angles. So suppose that we have a quadrantal angle of 270 degrees. So that's right here, yeah? Because right here would be 90 degrees, 180 degrees, 270 degrees. So here's our theta. Well, all right, and just for the sake of numbers to work with, let's give this a coordinate. So we'll say maybe this is, well, it's going to be 0, comma, negative 3. How about? All right, well then that means x is 0, y is negative 3, and r, you can check this yourself, is 3. Again, it's just r is just the distance from the point to the origin, which is, in this case, it's 3. It's easy, you can see it. So, all right, let's evaluate. Sine theta is y over r, so negative 3 over 3, which is negative 1. Cosine of theta is x over r, so 0 over 3, which is 0. Cool, no problem. Tangent theta is y over x, so negative 3 over 0. And negative 3 over 0, anything over 0 is indeterminate. So specifically, since we're talking about a function here, we say that the function is undefined at that point. So quadrantal angles, some functions will be defined, or some functions will be defined. They'll have a well-defined output. Others will be undefined, and it's going to kind of switch depending on whether the quadrantal angle falls on the y-axis or the x-axis. Let's see here. The very last things that I will say here are just be careful about the signs. So, and we saw this already, that, and this is the reason too that I think it's smart to make pictures rather than just go off of your mental image of the triangle that is being formed, because the sign of each trig expression, and by sign I mean like, is it positive or is it negative? That sign will change depending on if theta falls, depending on what quadrant theta falls into. So, just kind of abstractly, remember our quadrants, they start in the top right and then they move counterclockwise. So quadrant 1, quadrant 2, quadrant 3, quadrant 4. And since our trig functions are defined by x, y, and r is always positive, but x and y are not. They will be positive or negative depending on the quadrant. So the sign of each trig expression really just comes down to, are x and y positive, negative, or what? So in quadrant 1, both x and y are 0, which means that if we think about, so in quadrant 1, if we think about, say, sine theta, which is y over r is positive, y is positive, so in quadrant 1, sine of theta is positive. In quadrant 2, here, x is less than 0 and y is still greater than 0. So in quadrant 2, y is still positive, r is still positive, positive over positive is positive. In quadrant 3, this is where for sine things will change. In quadrant 3, both x and y are negative. So in quadrant 3, since y is negative, negative divided by positive is negative. So in quadrant 3, sine of theta is always going to be negative. And in quadrant 4, same deal. Even though x is greater than 0, y is less than 0, sine depends on y. So sine is negative in quadrant 4. Cosine of theta, cosine is x over r. So in quadrant 1, it's positive over positive is positive. In quadrant 2, it's negative though. X is negative, so it's negative over positive is negative. In quadrant 3, again, x is negative, so cosine is negative. And then in quadrant 4, x is positive, cosine is positive. Tangent theta. So tangent theta is kind of the interesting case, because it depends on both y and x. It no longer has the implicit positive denominator. Now the denominator can be negative, because remember, tangent is y over x. So at least in quadrant 1, nice and easy, positive over positive, tangent is still positive. In quadrant 2, we have positive over negative, so it's negative. In quadrant 3, negative over negative becomes positive. And in quadrant 4, negative over positive is negative. Whoops. Did I say negative there? It's negative over negative in quadrant 3 is positive. I can't remember. I either said it wrong or wrote it wrong, maybe both. In either case, quadrant 3 tangent is positive in quadrant 3. Yep. Okay, so there is that. Right, I guess the very last thing that I actually mentioned in this lecture is, and I just kind of stated this as a fact, the ranges of the 6 functions. So sine and cosine, their ranges are strictly between, not strictly, but they are between -1 and +1 inclusive. So -1 is less than or equal to sine theta is less than or equal to +1. -1 is less than or equal to cosine theta is less than or equal to +1. Cosecant and secant, since they're reciprocals, it's essentially like wherever sine is defined is where its reciprocal. Cosecant is undefined, and vice versa. Wherever sine is undefined or outside of the range, then, right, I guess not defined, but wherever sine is outside, whatever is outside of the range of sine, I'm like tumbling over my words, that's where cosecant, the range hits it. So cosecant is either, cosecant of theta is less than or equal to -1, or cosecant of theta is greater than or equal to +1. Same thing with secant. It's either less than or equal to -1, or it's greater than or equal to +1. Tangent theta and cotangent theta can take any values. They hit all values. Oops, values. So in other words, their range is all real numbers. And maybe I'll make another video explaining kind of deriving this or proving that this is the case. But for now, I think that it's best to just know that this is the case.